calculator, but now I share the screen with code, and here it is. And so what is supposed to do? So we first take a matrix, an array, a two-dimensional array. We have in one dimension we have everything constant, but in I direction we have a sinusoidal pattern. So amplitude changes sinusoidally. So it goes from -1 to +1. And then we start mixing those, so to say. The first row, in the first case, we shift all the pixels in the I direction as a function of j. So a new value of the matrix takes old value at the point I is written to the new position I plus something. And by the way, I think I figured out, guys, I figured out what is actually going wrong. I understand actually what is this code wrong, and I can write here as a comment. So it should be the other way around, because not to write here into C new from old C, but the other way around, because now if we take big A, sufficiently big A, then if we go to a next value of I, then we might jump over values in here, because like you take 50 and then we take 52, but we miss 51 in between. We write into new matrix, but we are skipping pixels. Okay. All right. So if we take the other way around, it should start working. Yeah, it doesn't matter which direction we shift, so we can just make it so that like that, and now it should be working much better. And then we need to do the same thing from with so as a result of this first iteration, we have shifted all the pixels into new positions. Now we take next, and then now we want to shift them similarly, but now in vertical direction. And so so we now we make it so that here and here, like that. Now we shift everything vertically, sinusoidally, and then in principle we can start repeating it.
Why are we switching
so after first step, our new values are written into matrix C new, and now after next operation, the new values are in C.
But now it's like the same plot that we had before, but it's just the colors are inverted.
So now you have something.
Not the same plot, but now the colors are inverted. It was before yellow, now it's just blue.
So it seems things are still not quite correct. But again, I think we need to stop discussing the homework here right now, because we still need to have discuss topics of the lecture, which we did not what we need to discuss. So Raido, how are you? Like you probably it's quite difficult to follow for you right now, because I don't know if you have managed to have a look what the homework was about, because that would have been helpful for you, I guess. Okay, so basically what we have here on the screen, it's something which should should work, but apparently there are still some mistakes because Siim has running it on his laptop. He cannot share, unfortunately, his screen, but the result is not quite what we want to have. Also, it's something not some features are more what we want to have, but some things are still not correct. Let us stop it here. Please try also to figure out what is wrong with this code here. But let us go on now to select topics of the lecture. Now, let me make new share then. And let us try to start discussing. So, Raido, did you manage to look on today's lecture? The lecture number 4 was it? Is there anything what you looked at it is not clear? So please ask, and then we can discuss it all together. So what it was basically, we were trying to derive equation which describes probability distribution function of the material element lengths. So we have a line and then we have a line, and then we stretch it, it becomes longer, and yeah, it's still not work. My touch screen still does not work too well, and then it might become at certain moment short again. Oh well. I think let us work in like we did last time. So I show my screen and point my camera on the screen. Yeah, really stupid way of doing it, but let us do that way. Switch on the screen. The lights. Yeah, the whiteboard. Something like that. So we have material line, which becomes longer and longer. And then we want to write a certain probability distribution function, which describes how the length evolves, but in logarithmic scale. So we take L divided by L not. I think we denoted logarithm of it's like L capital, was it? Something like that in selection. And then we have a probability of finding the lengthening by a factor of L equal to a certain function f of L times dl. So if we have from L to dl plus dl, then dt probability of having a material line length in that range is given by this expression here. So f of L is a certain probability distribution function. And then we use certain like mathematical techniques to first describe it like a convolution that we can just consider correlation time, and then a new so we have certain let us suppose everything has fixed length. So we start with f as so this here is f, here is L, and we start with Dirac delta function. So we have definite length of our material line, but then it starts being stretched, and now we have certain during correlation time something definite happens with it. So we can calculate in terms of convolution over correlation time, and then we have difference equation. Basically, new value of f is expressed as a convolution of old and a certain convolution core. This was what was in lecture. But then we simplified it and obtained a simplified differential equation in the form something like that: df over dt plus certain v df over dl equals certain d square f over dl square. Can you see, Raido, is it more or less clear what is on the screen? I'm not so sure if you can see it. All right, and then, which means that this profile here would evolve something like that, something like Gaussian profile. And then the talk went as follows: that now this thing here, equation actually cannot be exact. And the reason is that we have a kind of biased random walk was a logarithm of the length. During each correlation time, our line becomes a certain average number of times longer, but it is not definite. Sometimes a bit smaller, sometimes a little more is the length. So it is a kind of random biased random for L. So L starts at this value, and it becomes longer, but less longer and more longer. And that's why the center starts moving, and it becomes, as a distribution function, becomes also wider. And now, if we want to go, during first lecture, we derived a diffusion equation based on random walk. And it kind of works, and you can substitute it with, describe it with random walk, assuming that the steps are shorter than the profile width. So if profile is wide enough, then we can describe it. It was random walk.
So
Yes.
one more time, why can't this equation be exact?
Yeah, why it cannot be exact? Now the reason here is that the assumption when this becomes exact, it becomes exact when you have time, the step length of your random walk is much smaller than the characteristic scale of the profile of this PDF. So this equation describes PDF. When we derived the diffusion equation, you remember we applied Taylor expansion. Taylor expansion means that we have something small, and so that something small was a step length as compared to the characteristic dimension of this profile. And here you have always some parts where this is not satisfied. So it's like because it is in a logarithmic scale also. So yeah, at the very least, you have here at this range, yeah, characteristic scale becomes so although this fits here will grow, and it becomes like the characteristic scale becomes larger and larger and larger. Even though we have here and in those ranges here, you have always a small characteristic range when you have crossover from this big part to the very small part, where it becomes very small, exponentially small.
So basically, the head and tail of the function.
Yeah, tails have always a short characteristic scale. Yeah. Oh, sure. I myself him. All right, I don't know. Just I was moving wrong camera. I already forgot which camera was showing my screen. Is it okay now? Not very. Maybe I switch off one camera and showing only other, because I myself am trouble figuring out which one I'm showing. Let me pin this one. Yeah.
The picture is the same as before. Yeah. Yeah, that's the one.
Is it okay now?
If something was below, then I cannot see it yet.
And so we have this equation here. But this equation is which describes the probability distribution function of the length is this is only approximate if we have considerable correlation length for the velocity field. Now, why actually we are so much interested in this probability distribution function of the lengths of material elements? You remember these are the same as gradients from the last lecture. These are the same as gradients. So once we know this distribution, we know also about the distribution of the tracer gradients. And now this equation becomes precise if we have very short correlation time for velocity field. Which is when you have you imagine one snapshot velocity field and almost at the next moment of time it already is completely different. So this is actually a model which is very widely used in turbulence studies. This is called Crichton model. Greishnan model, which is delta correlated in time. So what does it mean, delta correlated in time? Do you more or less understand? No. So delta correlated in time means that actually we have some kind of delta correlation when you go back to the first lecture. There, the white noise was also delta correlated in time.
Does it have something to do with the autocorrelation function that we have?
Yeah. This is actually, this is autocorrelation function for the velocity field. So that what this does mean is that if we take velocity at certain moment of time t at certain position r, and now calculate autocorrelation function at certain moment t prime and r prime, then this an average over an ensemble of realizations. Then this becomes something which is delta of t minus t prime. And if we have now isotropic turbulence, so this correlation function is independent on direction from r to r prime and depends only on the distance, r minus r prime. Okay. So autocorrelation function is now, yeah, I wrote it actually fixed. D and certain function g of which depends only on r minus r prime. So it is a function of the modulus of the distance from r between the of the distance between the 2 points. And as for time, as long as t is different from t prime, they are not correlated. The result is 0. But if t is equal to t prime, then it is infinite. Now, why do I need to have infinite? Well, you imagine you have velocity field, and it carries you somewhere. And this delta correlation in time means that at each next moment, it forgets its previous state. So you would be moving randomly back and forth. It would be Brownian function, right? Velocity field would move you back and forth randomly. And now, if you imagine that you start reducing the correlation time steps like that. You start with something which is not small, and then starting in making smaller and smaller and smaller. And now, if you want, imagine that it's the end effect of the velocity field would be carry something to somewhere. As you increase, as you like directed walk becomes random walk, you must start moving slower and slower and slower. To reach still the same distance, you must compensate for it, make it bigger. So, in order to have the same effect, you need to, while reducing the correlation time, you need to make the velocity field bigger. That's what. That's why you need. And if you go to the limit of correlation time go to 0, then actually amplitude must become infinite, and that's from where the delta correlation comes from. So now, why I'm speaking about this? If whenever you open some theoretical studies, then you might happen to on some papers on using Greishnan model. Why they use Greishnan model? The answer is that analytical studies become mostly possible if you have Greishnan model. Otherwise, it's very difficult to advance analytically, make like strict theories. Now the question: if Greishnan model is such like strange things that velocity amplitude goes very big, infinite. It's kind of, it doesn't at all seem similar to real velocity fields, right? Very wild distortion of the real life. Real life is that velocity field is moderate and carries somewhere, but now you have models that your velocity field is very big, and but it forgets itself very fast. So you move by infinitely small amount, even so during each correlation time, even so velocity field is very big. So how comes those two things can become, how comes the Greitner model makes any sense? The answer is that actually it doesn't matter in terms of diffusion how the velocity field moves you. See, what is important is if it has the same stretching statistics of material lines. So in terms of turbulent mixing, what matters is how material lines become stretched. All the rest is not important. And if this Greitner model like that does provide more or less the same statistics of material line stretching, then it is okay. Then it's like a model which has connection with the real life.
One more thing, what is being stretched, or why was it necessary? Why was the Greitner model?
What matters is a stretching of material lines, material elements. Like you paint a rectangle on water, and water is being stretched, and you look how this rectangle evolves. But the rectangle is very infinitely small, so it remains rectangle at its beginning, right? So what matters is stretching. This we learned more or less yesterday, but during the last lecture, that we saw that a gradient behaves the same way as the lengths of material lines. And that's why the stretching statistics matters. I showed you also a figure where you had, like from the experiment, you had regions where a lot of stretching, where gradients become very big, and regions where it's stretching is small and the gradients are not that big. And so what matters is stretching. And so now, now the situation is that this real life is something for in terms of PDF is something close to that, but not quite exactly. So this equation becomes from the Greitner model. In real life, it is slightly different. And to be completely correct, you would need to have actually here you will need to start adding here correction terms. So if in the lecture recording, last lecture recording, I think we had something like a Taylor expansion, something. So if we have to try to do it, we have first we start off with convolution equation for f, and then we try to go to this some differential equation. But we then to do that, we go first to Fourier space, because if we have convolution equation and take a Fourier transform, convolution becomes product. Am I jumping too much?
Why was Fourier transform?
Again, maybe again, yeah.
Why was Fourier transform?
Okay, so suppose we have equation something like that. df over dt equals, let us say, integral of f at x minus psi, just arbitrary equation, not necessarily related to which it was what we have here, just arbitrary equation, and g of psi the psi, something like that. So we have convolution of f with g. Okay. Now, how to solve this equation? No one taught you, right? In mathematics, have you met equation like that? Now I can see that reflection is on the screen where I wrote it, but I'm not much in the position to help improve it. So yeah, how to solve this kind of equation, such kind of equations?
It was yeah, the last thing we took in like Janos lectures. But,
Yeah.
memory is a bit easy there.
Yeah. Okay. The trick is that if you take Fourier transform of this, and then convolution becomes product. If you go to from Fourier space, so this equation becomes now EF tile, where this is Fourier transform over dt equals F tile and G tile. And now it is in K space. These are all functions of K. So whenever you have a convolution equation, take Fourier transform and you can start solving it. But of course, then you need to go back again. And the procedure, how during the, in the lecture recording, how to got this equation was that we had to begin with, we had a convolution equation which related f at certain moment to f at one correlation beforehand. And then we applied Fourier transform to get rid of convolution, to get convolution into product. And then we had a kernel J, which like it was a correlation, described correlation, time correlations. And then we expanded this into Fourier into Taylor series. And then we were able to solve it and go back to the physical length space L. And then because we had Fourier transform, so this corresponds to first term of the Fourier transform, this corresponds to second term of Fourier transform. And that's how we got it. But to be very strict, we could have kept here more terms. So more terms may include. Actually, we could hope the more precise it becomes. Is that right? So use that if you have Taylor expansion, you can keep more terms, and the result is better.
But there was this thing in the lecture, like you can only take like only the two terms, because if you take more than
yes. And now we are exactly at that point. So so we are saying that this equation here describes delta correlation. This works for velocity fields which are delta correlated in time. If they are not delta correlated in time, this is not precise, and to be more precise, we would want to have more terms. But now comes into play what is known as Paula theorem. Paula theorem states something. Oh, I think I write something like that. And what it states is that, well, what we have here is called Fokker-Planck equation, like the equation describing probability, evolution of probability density function. This Fokker-Planck equation. Now, Paula theorem states that for Fokker-Planck equations, you either have two terms here, derivative along x or l or whatever you have here, either two terms or infinite number of terms. Only two options, because if you have something more than two, but less than infinite, like you would want to have here something like maybe something like some kappa multiplied by d cube f over dl cube, maybe. Or perhaps we hope that this makes it more precise. Yeah, somewhat it can even improve, but what problem if you add this term here, then what goes wrong is that this f might become negative. So probability distribution function must be always positive, and integral must be unity. STL must be unity. But if you add here some number of additional terms, if it is not infinite, then you will always have possibility depending on the initial value of that f, which shape f is initially, you have always the possibility of having negative probabilities, which is not physical. So the problem is that and yeah, if you have two, then you are just sure that if f is initially physical probability density function, always positive, integral 1, then it remains always so. You can make differential, so such kind of equations with infinite number of terms, and then again the same applies. If it's a good equation, if f was initially positive everywhere, it remains always positive as well. But as long as you have add here a certain finite number of additional derivatives here, then this no longer is the case. You can always figure out such f, which is initially physically plausible, meaning that always positive, but it evolves into something which is unphysical, which means that negative probabilities. Okay. And so the situation is that the Grantham model is as good as you can go easily, and if not, then we can just give up with this kind of equation, and we can use instead what is known then is a large deviation function. And this is towards the end of the lecture. Mul loen käib siin. Ja ma olen majas, mul loen käib, ma helistan, kui läbi saab, varsti saab. Teeme nii, no, see. All right. Now, is that part more or less clear? So, what is large deviation function? Okay, now this thing here, how you can look at this thing here?
I would just like to clarify, to write it down. So the Paulow's theorem says that in our equation we can either have two terms or an infinite number of terms, because otherwise the probability
might become unphysical, meaning negative, take negative values. But probabilities are always positive, right? Mm. It would be nice to have negative probabilities, but okay. So yeah. Sorry. A certain type of function. This applies to Fokker-Blank equations, which means an equation describing probability density. So f is probability density function, which means that f times dl gives you probability. And so it means that f dl must be always positive, which means that f must be always positive, or non-negative, not positive, but non-negative. So you can always, and we assume that integral of f is 1. It is quite easy to see here that if it is integral 1, it remains 1. Because you have this equation, even if we add here more terms, integral is conserved. Can you see it? That the integral is conserved. So let's just take this equation here and integrate left and right hand side parts over L. So integrate this over dl, and what we obtain is that d over dt of integral f dl equals, and now integral of those things over there, integral of minus d df over dl plus d square f over dl square, and so on, and all dl. But this is in zero because you can integrate by parts. All right, because this is derivative by L dl. So it's different of f from minus infinity, from minus to plus infinity. But if f is equals, it goes to zero, both minus and plus infinities, it gives you always zero. So integral of right hand side because of that becomes zero. Which means that time derivative of f is 0, which means that it remains constant. If it was 1, it remains 1. Now, any other questions here?
There was this part of like spectral flux when there was talk about bachelor's law. I didn't understand what it was, what it meant for us. Just from another individual.
Yeah, the spectral flux.
We had like spectral theorem, and from there.
Yeah, we derived Bachelor's law. So Bachelor's law was also the topic of this lecture.
Yes, it was a good part.
Yeah. Okay. I think because we now there is already not so much time, so maybe and spectral flux, in order to make it quite clear for you, I think we need a little more time. So maybe it's better to explain it next time, because otherwise we will not finish, or otherwise we will go a lot over the scheduled time. But just yeah, let us keep in mind that we need to have next time to talk about spectral flux. Why? Because this spectral flux is very important, and this is going to be in particular for the Kolmogorov turbulence into it. Because if anything from this turbulent mixing, what you should learn is what the Kolmogorov turbulence is about, and this is all about spectral flux. So that's why we just need to take our time to understand it. And now there was the thing about the statistical conservation law here also, right?
Yeah, there was something about that.
Was that part clear?
I guess we can go over it. There was the only part that I understood that was we had some square and we started like stretching it, and it.
Yeah. All right.
Yeah, not really good.
Yeah. All right. So now next time I keep up with my my touch screen. So my touch screen it appears it doesn't work in any case. So I better do from the beginning as we do here. I do have actually another like drawing board which I can in principle use. But it's like I need to carry it always, and that's a possibility. But it's maybe it was done in such case, and so maybe sometimes I need to do it online our elections, and I'll be using them. Now, statistical conservation law. So we learned that if we have real flows which can describe to some extent using Greitner flows, which are easy to analytically describe. And if we have, okay, let me write here, Greitner flows. Many analytical results. You can just, we don't have enough time to go all through, but just you have many results. Many analytical results. You can just go through and use them. But you need to keep in mind that they are somewhat good, but not if you need to have very detailed match, and you might not have it because there are some differences. And now real flows. One thing what you always have is that large deviation function. Which describes the statistics of the stretching of material lines, basically. So if we have that diffusion equation, we have diffusion, you remember, or PDF was described in the scale where you have a horizontal axis is the logarithm of length. And so it was e to the power of minus, and then L minus Vt, so L grows, midpoint of L, also T, grows as Vt squared divided by some 4 dt. So this is PDF of Gaussian browser, of the Brownian walk. So midpoint moves proportionally to time, and denominator describes the width of the profile. The width of the profile grows as square root of dt. So so that's it. So this is the green function of the diffusion equation. I think we introduced this during the first lecture. So this is how the PDF of lengths behave if we have Greitner flows. This is PDF of lengths, logarithm, log of lengths of material lines. Okay, and for Greitner flows.
Logarithm of length of
Log of length of material lines. So logarithm of length is from material lines. So lengths grow. L logarithm grows linearly, which means that it itself grows exponentially. So that we have like what is called Lyapunov exponent. Lyapunov exponent describes exponential growth of something. So here, length itself grows exponentially, is described with the Lyapunov exponent. If we speak about logarithm, so we have this kind of solution of diffusion equation. But now this is only for Greitner flows. If we go to real flows, then this is substituted with the large deviation function. So here we have something like e to the power of minus h of now something like that. Minus t h of L divided by d. And h is called large deviation function. Now, what is funny thing here is, so okay, so L divided by t, what it is? L is logarithm, right? Logarithm of length. L divided by t is logarithm. Let me write here like that. L is logarithm of L. So L divided by t is logarithm of L divided by t.
in the beginning you wrote.
Sorry?
In the beginning you wrote that big L was logarithm of L divided by 0.
Yeah. Okay. To be strict, yeah. Just assuming that L0 is unique. Now, if we divide this by t, then we obtain, which is, let us keep in mind that at least here we see that L grows linearly in time. So if we divide this by t, we obtain what is called like it is essentially like finite time Lyapunov exponent. Length, logarithm of length divided by time gives you the gives you the okay. Sorry. So if we express from here, Yeah, basically that L divided by T gives you finite time Lyapunov exponent, logarithm of the length divided by time. So if length goes exponentially in time, then logarithm grows linearly in time, and if we divide by T, we would obtain Lyapunov exponent. But now we call it finite time Lyapunov exponent because Lyapunov exponent is theoretically at the limit of infinite time t. But here we will not considering infinite t, big T, but not infinitely big. So that's why you say that it is a finite time Lyapunov exponent. So that L divided by T is finite time Lyapunov exponent, FTLE. And so you can see that we have probably this real function is a certain function of finite Lyapunov exponent, but it will grow also is multiplied by time t. So it becomes as long as age is positive, it becomes smaller and smaller and smaller in time. So now, if we have real flows, our PDF is Gaussian. If it is not, if it's real flow with some finite correlation time, then that must, to be exactly correct, that must be substituted by with a different form where we have arbitrary functions. So here is quadratic function, here is arbitrary function, right? So a quadratic function is what we obtain from real flows. So h, which is in general more complicated than quadratic, now becomes quadratic. So we can plot h as a function of h here, something like that. So it is upside down. Yeah, normally it would be a parabolic function, but now it is non-parabolic, but it's still somewhat resembles parabolic. But yeah, I guess it needs to go through here as well. Something like that. Yeah, it can be like that. All right. So actually, I don't think the large deviation function business is too important for you. Just you know that there is such a thing. So just you know that there is such a thing that if you really need to go into specifics, then instead of Gaussian distribution for the logarithm of the lengths, you will have something which slightly departs from it. So let us stop that large deviation function thing here, because yeah, for you it's enough to for you to be aware that there is such a thing. Now, yeah, and now you're already packing your things. So we did not now discuss about the statistical conservation laws, but I understood that you more or less still understood it from the lectures, was it? Kaspar? You didn't reach a theme. How was it? More or less understandable?
There was quite good conspectus on the overview.
Okay, yeah. All right. If the concept was quite good, then maybe it's okay to skip it here we're discussing. But keep in mind that we have homework on the statistical, like on the distribution function thing. So I think we would keep that homework, which was given in the fourth lecture.
Yeah, also for maybe it's a bit too much. If you have like, let's say, you have to review the lecture, which is like 2 hours at least. And then, for example, today we had like the big project, and
okay,
working, we're gonna have to
okay.
Again at home.
Okay, all right. I can see the point that actually a big project itself is taking too much. That in addition to that, also doing some homework become
More useful.
Yeah, that's right.
More homework.
Yeah, so if we do 4 hours of lectures per week, you get your bigger homeworks and then presentations, that should still be quite fair.
Okay. So still, I think from time to time, I still would like to at least some homeworks. I would still like to see, but we can skip at least some of them. So all right, let us skip then the homework related to the this PDF. So basically, what was homework about? It was to find out how the certain power, the distance between 2 points taken to a certain power grows in time. So this guy here describes the distance between, the length of the line, but also you can imagine of 2 points being at the end of the line. And you can then L is the length between the 2 points. And then you take L to the power of n and take average and see like different average over different realizations and want to know how this starts growing in time. And to say that we expect this to proportion to certain power t to the power 5 pi, and we want to find what is alpha. And the procedure is to take L and distribute this PDF, and then take integral and calculate. Basically, that was homework. Checking if you understand what is probability density function, applying to the calculate average. But okay, let us skip then from this lecture and instead the wide concept projects. Okay. All right. Raido, how are you? Raido. Yeah. I'm not sure. So just let us take a little bit of time and discussing that. Is it going more or less okay? Because I kind of feel that our consultations maybe today, of course, we spent half of the time on the coding, which I'm not sure was the right thing to do. But
Is it possible to like talk to the consultation or maybe on Zoom or something? So maybe we can just at least do the bare code that so we can see we compute the values and then at least we can do the plotting of solution like whatever way we use this. But we just have like a working code basically like the consultation. So,
yeah, well,
so you can maybe we can go through yes, do programming and see if we can do it for you. So
yeah, you can. Well, as for homework, now we kind of made some progress. You learned about bitwise and how to use it, but then we still have some bugs, which is very typical for coding. Now you need to start debugging and see what goes wrong. So now, did you have any debugging during your Python? Probably you did, because how to figure out how things go wrong. What we did here actually was first step of debugging. We just print out picture at every time step. So you can try changing parameters, making that amplitude smaller, and see changing parameters, playing with it. You can. So I suggest that as for that coding homework, you should be able to at least please try to figure out what goes wrong.
it's kind of hard to figure out because I still don't know what equation precisely do I have to use to plot it. It's like we kept chasing C new and C just willy-nilly. It didn't make sense anymore. And I still don't know what's the concrete like equation I have to plot. Or like
if we take the I think we had some homework as a project discussion in the last video recording of the first lecture. I can open it.
There was something, and I think it's a bit different from what you told us. is it C?
Lection number 4. And see here at the end we had something shown. No. Why don't I see it? I think there wasn't. Ah, yeah, now here at this place here. Okay, this is more or less how it should look like. You start with the. I need to share first. I need to share first the screen. So so you need to, first you need to have you start with this, which you basically had, and then you stretch in one direction. It becomes something like that. Only stretch in one direction, and then you stretch in another direction. It becomes like that. And then again in the first direction, and then again in the second direction. I think this code here also some bugs. It becomes like too much medium blue here, so it's not completely bugless code, but better than we had. So at least this first time step is completely okay. Second time step was also more or less okay. Okay. So Siim.
It doesn't really fix it because like you can show me the end result, it's good
Yeah.
and great and all, but still like how do I do it? Like,
How?
you can like show me a random like, exponential function. Okay, it looks like that, but what exactly?
Yeah, okay, well, you see, you need to carry out pixels from one point to other as shown in the figure. You need you see initial state and after one time step. It was like vertical blue isolines, and then at next step, pixels were carried over horizontally.
Yeah, but how?
All right, what we can do, we can next time we can come here a little earlier. What about it? Next time is because we as today what happens that 1 hour is a little too short time to go all the topics of the lecture, right? Do you agree? So today we had only, because we spent 1 hour on the code, then only 1 hour was left, which is a little too short. So next time, let us, if you want to discuss the code, let us come a little earlier, like half an hour earlier. 1 hour earlier.
Our lecture before that is at 1.
Okay, then half an hour earlier, yeah. Then we have half an hour to discuss the code.
We can even come an hour.
Huh?
We can even come an hour. Yeah.
An hour?
Earlier.
1 hour earlier. If you like, we can come.
Yeah.
All right, let us do that way. Let us come then next week. We meet here 2 o'clock. Now, Raido, what about you? Will you be also joining our Zoom as 2 o'clock? All right, so let us schedule. Then we have like next time we will be having 3 hours, out of which during one first hour it will be like a kind of consultation on the topics which we already passed, and you might have questions, and the code and the coding homework. And then the last 2 hours will be on the lecture number 5. All right, then see you. Bye. Bye.